All right. So thank you for waiting for this exciting talk, and thanks to organizers. Do they hear well? Yes, I think. So, and thank organizers for inviting me to give this short tutorial about distributed computing. So, so most of this will be about theoretical things. There will be some practical things, but most of it is about theoretical computer science. And also, I will be very theoretically talking about it because I will be pointing from here to there because of this cable. You know, it already said that the organizers keep us on a short leash here. Anyhow, so I will talk about. So I'll talk about two different fields. One will be combinatorial topology and one distributed computing, and I'll say how they merge or how you can use the methods from combinatorial topology in distributed computing. So first, very quickly, I'll say a few words about combinatorial algebraic topology and how we think about this. So you know, there is this journal Notices of the American Mathematical Society with little article every now and then, which is explaining different concepts, and it's what is, and it's what is this, what is that. So what is combinatorial algebraic topology? So in combinatorial algebraic topology, classically, we're computing invariants, the classical invariants of algebraic topology, with the difference that we have combinatorial cell complexes, and the methods which are used were combinatorial methods. So in this language, so combinatorial cell complex would be some cell complex where all the cells have names, combinatorial names. And by combinatorial means would mean that we do some operations with these names and understand something about the topology. Okay. So just to say a few words about this specifically. So a combinatorial cell complex would be the following structure. So a cell complex, there would be two notions of being combinatorial. Okay, it could be locally combinatorial and globally. So locally, so the cell complex in general would mean we just take cells, which could be some objects. It depends on what we do. We could take topological balls, or we could take simplices, or we could take direct products of simplices, or some other things, direct products of permutahedra. And then we would want to glue them together. Okay, so if we take balls, for example, topological balls, and try to glue them together by continuous maps, then of course there are very, very complicated ways to glue them together because there are very many continuous maps between spaces. So if the map is quite convoluted, then even having only 2 or 3 cells to glue together, we can produce quite complicated objects. So in a situation like this, we wouldn't want to analyze. So we would want to have something which is locally combinatorial, which in the optimal case would mean we actually do not need to specify the continuous maps themselves, but we only need to say which cells are glued to which cells, and the rest would be able to derive just from the descriptions of the cells. So in the simple case, if we have simplices and we glue them together, if we just say which simplex is a boundary on the boundary of the other, we already know what the gluing map is because we just need to order the vertices, and there's a standard way to do it and identify everything very nicely. We don't want to deal with convoluted maps. So in a situation like this, we would say that it's locally combinatorial. However, in combinatorial cell complexes, we need the second thing, which is the globally combinatorial cell complexes. And this means that we have an enumeration of all cells by combinatorial objects. And moreover, we also have the notion of taking boundary of the cells also in terms of this of these labels. So just to give you an example, if I had a graph, for example, and I would want to color it with n colors. Let's say n is large, so I'm able to color it. There are many different ways. Then I could produce a cell complex whose vertices would be all graph colorings with this number of colors. And then I could produce a geometric space where this would be vertices. So I could continue. I could say the vertices are just the graph colorings, and the edges would be, I would connect two vertices by an edge. If I would have two graph colorings which are different only in one vertex. So that's actually standard object, which is called graph of, in this particular case, would be graph of graph colorings. More generally, the notion of graph colorings can be generalized to the notion of graph homomorphisms. And that would be a graph of graph homomorphisms. And that's something which one studies in combinatorics very much. In topology, we would want to take the next step and go higher dimension and say not only you want to connect to graph colorings which only differ in one vertex by an edge, but also if we have three graph colorings and they all differ only in one vertex, we would want to glue in a triangle. That would be one more thing. In dimension 2, we could also do one more thing, and this would be if we have a graph coloring, and we have two different vertices quite far from each other, and we change graph colorings in these vertices, and in two different ways, we would actually get a rectangle, which we also glue in, and so on in higher dimensions. So I'm not going to talk about these objects, but this would be an example of a combinatorial cell complex. So it would be, so just 2 weeks ago, I was in Dachstuhl, which is in Germany, a center for conferences for computer science, at a meeting on constraint satisfaction problems, which is a sub-subject in theoretical computer science. And actually, these particular home complexes have found quite substantial applications in this field, understanding the complexity of CSPs, the constraint satisfaction problems. So these things have been applied very much in theoretical computer science. So the field is quite large. I mentioned here a book which I've written some time ago about this combinatorial algebraic topology, where different constructions of this type have been studied. Okay. However, what I want to talk about today would be to go away from the sequential model of computation to the distributed model of computation. And this is something which I want first to, well, since this is a tutorial, I want to first talk about what kind of models that we are interested in distributed computing. So forget about the topology for now. Okay, so what we have is the following setting. So like I said, so theoretical distributed computing is a very large field. Okay, so there are very many different models. We need to specify something. So in general, we will now start with something general and then go more and more specific until we can get to a point where we have simplicial models, topological models. So in general, let's imagine the following situation. Okay, so we have n processes performing a certain task, and they communicate to each other, and through this communication, they want to solve this task. Okay, so in this model, the local computational power is not as important. The tasks are not of the sort which will require strong computational power. They could be of the sort that they simply agree on some value or something like that. So the local computational power is of no importance. So then the different models of communication between the nodes. So one of the classical one in the networks is called message passing. So you would have a network and different nodes would send messages to each other. And you would need to formalize this further. Okay, so there are different formalizations, different axioms of communication. I don't know. I mean, I can tell you an example of such an axiom that if A sends a message to B and then sends another one, then if they arrive both, then they arrive in the same order. That would be one axiom you could possibly impose on such a communication. So certainly you want to, if you want to do anything interesting, you don't want a model where you know for sure things will arrive. You want to have things that they may arrive or may not arrive, maybe even with errors. Another model of communication here on the list, read-write. That's actually the one which I'll be talking in this tutorial about. So read-write model means that you have this n processes and they communicate to each other using a common register of information. So each one has two operations it can perform. So it has some information. It can write its information to the register, to its part of the register. And the other operation it can perform, it can read from the register. And for complexity issues, we assume it reads the entire register at once. Okay, so those are two operations. So it can either write its own information into the register or read the whole register. And then there are other technical things. For example, immediate snapshot is what I just said, that it reads the entire register. Then you can also allow other primitives. So in the field of computer chip design, you can ask for more. You can implement on the hardware level different primitives, which your computation will perform very quickly. And you can ask. They're different, like you read and write immediately, or you read and check, and there are all kinds of different primitives you can implement, and they lead to different models. We're not going to talk about this. There is a large choice of possible failures you can have. So you can have crash failures. That's actually the most standard one. So the crash failure means that a process sends information. It may crash, which means it will stop sending the information. But that's really all that can happen. So you will not hear from him. But also there is no limit on the time, so there is uncertainty, because if somebody does not reply, it's like, if you're an organizer of a conference and you ask somebody for an abstract and he doesn't reply, you don't actually know, is he very slow or does he crash? So you have to make a decision regardless. So that's a kind of uncertainty you will have. Other type of failures, worse failures than that, are Byzantine, so-called Byzantine failures in this distributed computing. So a Byzantine failure means that the process sends malicious information. So you hear from him, but he may corrupt his information, may have been corrupted by the communication, and you would still need to somehow solve the common task. So that's actually harder, because you get information, but you don't know if the information is correct, right? So if you have, I don't know, financial reports from different EU countries, and somebody sends financial reports for 5 years, and eventually you find out that they were all maliciously corrupted. That's an example of Byzantine failure in communication, right? So typically protocols which would solve tasks like this would solve it by some sort of majority voting. So under assumptions that not too many things get corrupted. Of course, if the whole network is corrupted, then there's nothing you can do. But if not too many are corrupted, then the healthy ones may communicate to each other and still get to the right decision. Exactly. And then the different choice of timing models, asynchronous and synchronous. So asynchronous is more interested when you don't actually know exactly how long things take, but you have some axioms to have it controlled and you can prove things. So that's a general kind of system. So one standard model of communication. Okay, so just before I proceed, so there's different model of communications from the complexity point of view, from the theoretical point of view. There are different results connecting them and reducing complexity from one to the other. So I'm not going to go into this, but then the advantage of this is that you can actually just get fixed on one model and know that if you prove things about this one, about impossibility results, about complexity results, then other models of communication will be reduced to this one. So the standard model of communication, which we look at, is the following. So like I already said, the processes communicate via shared memory using these two operations. One is called write, process writes its state to the devoted register. And one is called snapshot read. So the process reads the entire shared memory in an atomic step. So atomic steps means nothing happens during the process. Okay, so that's the big problem with all these things, is that somebody starts to do something, and until he's finished, someone else starts to do something. You know this from right? So atomic step means it's atomic step. So snapshot read, he reads the entire register and nothing else happens. Okay, so we allow crash failures, which means if we don't hear from somebody for a very long time, it's okay. We just deal with it as if he's maybe slow. We cannot distinguish between the two anyway. So that's maybe one way to deal with it. If somebody doesn't reply a long time, it doesn't matter if he's slow, he crashed. I think he's crashed. Anyway, so all protocols are synchronous and wait free, meaning there are no upper bound on how long it takes to execute a step. And so all executions are immediate snapshot, which means that at each step, a group of processes becomes active. All processes in this group first write and then read together, and so they proceed. And then the executions are layered, meaning that the execution is divided into rounds. So in each round, each non-faulty process reads and writes exactly once. Okay. So maybe let me look at an example. And then, so first I want to look at the example, and then I want to connect this to simplicial models. Okay. So actually, like I said, there are many different reductions. So in our reduction, it will be like this. So all the executions, so even the crash files you can reduce to this, all the executions will be like this. And each, there will be rounds like this. And in each round, each one executes exactly one. And it will be like this. At first, there is a group of guys who execute, they do it together, then another group, and another group, and another group. And in each round, it repeats for all of them. So even with crashes, you can reduce it to this model. Okay. So this means that combinatorially, each round, all I need to do is to have an ordered partition of my processes. So each round, I just say group 1, group 2, group 3, like boarding groups at the airport or something. And the first group, they all go and they write the information in the read, and the next one they write in the read, and so. And then, but the next one it repeats. So you see that the guy who was the last, let's say the guy who was first in the execution, he does not know what the consequent one will write, but he will know in the next round because they have already been there. So anyhow, so let's do an example. Okay. So one example is assigning communication channels, but there are different formulations of this. This is a series one. You can also say you assign in the airport, you assign the landing strips to the incoming planes or something like that, which is also a good one. So you have processes which use shared memory, and they need to coordinate among themselves the assignment of unique communication channels. So it means the following. So just like in the airport, so you have some designated number of communication channels, of which there are few. The number is not big. I don't know, 2, 3, maybe 10, something like this is the order of magnitude of number of communication channels. The number of possible clients which can come and ask for a communication channel could be in the millions. Okay, so I don't know, thousands, 10,000s, millions. So you cannot like have a designated channel for each client because the number of clients is very, very large. So just like the planes trying to land, there are many, many possible plane numbers, flight numbers, but very few passes. Okay, so you have to do it in a dynamic. So each time the group arrives, you have to assign them somehow by communications. Okay, and you cannot rely on the particular values of their identification numbers, so their flight numbers, but you're allowed to compare them with each other. So you're allowed to say that this guy has a higher ID than the other guy, because you have to distinguish between them somehow. And so, for example, in this model, which we were talking about, you can show that if you have 2 channels, it will not be enough if you have 2 processes. If you have 2 processes, they will not be able to understand each other. So here is an example how 3 channels is required if you have, so 2 processes mean arriving at the same time. So the bound is on how many of them can be there at the same time. Total number is very large, but how many at the same time? So let's say if you have 2 arriving at the same time, in this communication model, and you have 3 channels, then here is an example of what's called a distributed protocol, which will solve this task. It's also the optimal solution in this communication model. Okay, in this so-called standard communication model. Okay, so let's go through this. So you have 3 channels, C1, C2, and C3, and the protocol does the following. So the process writes its ID into shared memory, and then it reads the entire memory. Okay, so if the other process didn't write its ID yet, so he doesn't see the other guy, then he picks the first channel. If the other process wrote his ID, then he compares it, and depending on which comparison he has, he will either pick C2 or C3. So that's a very short protocol, and you would need to play around with this to kind of understand why it will not work. That, for example, here he would pick between C1 and C2, right? Because, well, let's just do something like just to play with this. Let's say in the third step, I would say, why pick between C2 and C3? Let's say he compares and picks C1 or C2, okay? So then the following could happen. So let's say he would pick C1 if his ID is smaller. Okay. Then the following could happen. And the first processor comes first, and he has a higher ID and he does not see the other one. Then he picks C1. Then the second one comes. He sees the ID of the other guy. He sees that his ID is smaller and he also picks C1. And then you have two planes landing on the same street. Okay, so that wouldn't work. Of course, that's not a proof. That's just a kind of understanding that this particular protocol will not work like this, but you can actually formally prove that you will never be able to solve it for two guys with just two channels. And for two guys, you need 3 channels. And for 3 guys, you need 5 channels and so on. But in general, it's not known how many channels you need. Actually, it's an open problem. If I ask, if I have n guys, how many channels optimally I need? There are protocols which do it in 2n minus 1, but maybe you can do better than that. So that's an example of such a task. Okay. So what are other examples? Here is a list of some of the most standard problems which one looks at in distributed computing. So the first one is called binary consensus. So in the binary consensus, each process starts with a value 0 or 1, and eventually decides on 0 or 1 as its output value. And the conditions are that the output value should be the same. And furthermore, if all the processes have the same initial values, then they must all decide on that value. So if they all have 0, they must output 0. If they all have 1, they must output 1. If in other cases, they can output either one, but they have to agree. Okay. If you didn't have the last condition, then you could write a very simple protocol, because you could simply, the protocol would simply say decide 0. So they all agreed on 0. Okay. And it would work in all of the cases except for 1, namely if they all had 1 in the beginning. Okay. So that's a standard protocol. It's extremely formalized here, but it's in all of applications. If you have, I don't know, a banking system of a network, and somebody's doing a withdrawal in some machine somewhere, you want somehow the whole system to agree either he did the withdrawal or he didn't. I mean, you may not give him the money, but if you did, you want to agree he did. So it's called binary consensus, and that's actually has been a standard task studied the other way also. So you could also say you fix the task and you study different communication models, and you would have theorems like binary consensus is not solvable in this axiom system of communication or in that, or if you add this primitive, then you can solve it, without it you can't, and so on. That's kind of things people do in this field. Binary consensus generalizes to so-called K-set agreement. So in the K-set agreement, each process starts with an input value within it. So it's the same as here, but you have at most K different values. So here in the binary consensus, you have at most 2. In K-set agreement, you have at most K different values. So the one condition is only values which appear as input values are allowed to be picked as output value. And okay, so K is the final one. So right, so K would be 1 here. Right, so you have, so an example of this would be, let's say you have 100 processes and they have different values up to 100, and the 99 set agreement would mean that they need to agree on some values. Doesn't have to be a single one, but it has to be at least at most 99. Some values does not appear anymore. So actually that's, of course, seems like a much easier task than a binary consensus, but there are theorems which will also show that this one is also not solvable in certain models. So you can't even agree on eliminating one value in this model. And the last task here, which leads to quite interesting, mathematics, is called weak symmetry breaking. So in the weak symmetry breaking, you simply have processes. They have no inputs, just the IDs. They have no values, but they have their own IDs, and they need to be distributed into 2 groups. So you could say they pick 0 or 1, depending which group they go. And the conditions are that both groups are non-empty. So that's why it's called weak symmetry breaking. So, well, weak it's because there's a strong, but symmetry breaking means you have to be able to break them into 2 groups. And your protocol should be comparison based, which means it's allowed to compare the IDs of 2 processes to distinguish them, but it's not allowed to use their numerical value or something like that. which makes sense. So find comparison-based way to solve to break weak symmetry into two groups. So for example, in this case, in this model, we understand the solvability. We don't quite understand the complexity for weak symmetry breaking, but for solvability, the answer is that you can solve the weak symmetry breaking if and only if the number of the processes is not a prime power. If it is a prime power, you cannot break it into two groups using this model. But if it is not a prime power, so the first case would be 6 processes, then you can break them into two. There's a proof that you can, but whether or not there is a protocol, it's a matter of discussion. Okay. Are there any questions until this point? So far I've been, this was like going directly into distributed computing, but I think in the school it is quite fitting. But so this is basically the world of this theoretical distributed computing, or let's say part of it. I mean, it's like I say, it's a large subject. I try to make a focus on a certain part. Okay, so basically solving the standard tasks in the standard model and also estimating complexity, which would be the round complexity because our protocols work in rounds. Now, how does this connect to simplicial setting? So once you start thinking about this, you start to discover many different structures, simplicial structures, both old and new. So it's the very first thing you can, notice is that if you look at this all possible initial configurations, this will give you a simplicial complex. So you can, so let's say in the very first simplicial complex you can find in this is the following. You have n processes, each one has a value 0, 1. So this will give you 2 to the n different initial configurations. And then I want to have a simplex for each initial configuration. So I will have 2 to the n simplices. And vertices will be just name of a process and the input value he has. Okay, so I could do that. I could just say, take as vertices name of the process, initial value. So I will have 2n vertices, right? And any compatible set of input values, I will put in a simplex. So what is a compatible set? Well, the only problem with if I pick values for different processes, the only problem I can come up with is that for the same process I pick 0 or 1. As this I cannot have. I must have either 0 or 1. Okay, so that means I have 2 to the n vertices, and then I have all possible simplices except for the opposite ones. So if you think about it, that's going to be a simplicial sphere. In fact, it's a convex hull if you just take n-dimensional vector space and take the vertices, the points on the coordinate axis with coordinates ±1, and take the convex hull, you'll get a polytope. It's a sphere subdivision. So that would be, that's the first example, maybe the simplest one, but still it's already kind of first example of simplicial complex. That's what we call input complex. Okay, so if somebody comes, so our task in the usual meaning, our goal is to translate this whole distributed computing business into simplicial language so that also the questions and also the open problems can be formulated purely in combinatorial language without referring back to the distributed computing, even though they not only would be derived from them, but they would actually be equivalent to them. So in fact, solving them in simplicial setting would be as hard but also as useful as solving them in distributed computing. So it's a one-to-one. Okay, but it's just much easier to understand simplicial setting and explicit conditions than vague defining of different models in distributed computing. Also because in the literature in distributed computing, oftentimes the conditions are not stated very explicitly, and it's sometimes hard to read off what conditions are actually assumed on the model. Whereas in topological, we have a culture of explicitly stating all the conditions and formulating everything very cleanly. Anyway, so that would be the output complex. Another one would be the input complex. That one would be output complex. So that would be all allowed final configurations. So in the going back to the binary consensus, allowed output configurations would be only two global configurations. Either all of them are 0 or all of them are 1. So that would be two simplices disjoint. Okay. Now comes the third part, which is the most interesting, and that would be a simplicial complex of all executions, which is so-called protocol complex. Okay, so that's a complex which is not associated to the task which you want to solve. It is associated to your protocol. So if I come up with a protocol of executions, then there will be a simplicial complex encoding that. So in this complex, the following will happen. So the maximal simplices in the protocol complex will be all possible executions. Okay, so unfortunately, since we are not anymore in a consequential computational system, we have more than one execution. So like I say, if they communicate with each other, I don't know, let's say if I had only two guys and they only communicated once, there still could be three possible things which would happen, right? Because it could be that the guy number 1 writes and then the number 2 comes, or the other way around, or they come at the same time. That would be 3 possibilities. And I would need to have a space of total space where all these possibilities would be baked in. Right. So actually, just last week, I was reading some little story by Jorge Luis Borges. I don't know if you know him. And he has a story which is called The Garden of 14 Passes. And in this story, he's trying to say that, you know, you could have a story where all possibilities which can happen are in the same story, not just one. That's exactly, so he was describing, of course, protocol complex. I'm not surprised since he predicted internet, so why not protocol complex? So you want to have like a simplicial complex, or maybe other complex, but in our case, simplicial, which would have all possible executions as top dimensional simplices. Okay. So what would be the vertices? So remember, in the input complex, the vertices were ID of the process and input value. Okay, so here in the protocol complex, it would be ID of the process, so you would know which process it is, and his view on the execution. In other words, what does he see as the execution unfolds? So if I have one execution, let's say I have 3 guys, so it means execution is a triangle. So I have a triangle, and the triangle says what happened. And then the vertices say for each guy, what did he see as things unfolded? But it may happen that in different executions, the same guy, some guy sees the same things. It may just happen. Okay, because maybe he was the first, things happened afterwards, he doesn't know that they did. So he has his view of the world. And so you would want to identify them. So this is how you glue them together. So in the protocol complex, you would have top dimensional simplices for all executions, and you would identify them along the vertices if the view is the same for the processes. And the lower dimensional simplices between would mean, you know, sets of compatible views of certain sets of the. So you can see it, I don't know, it's like some people now do some topology of the knowledge and so on, and in logic and so on. So this is exactly like it is in the protocol complex. So you can think of different simplices as views of the world, and they share, if you have a compatible group which has a certain view of the world, there may be different global views, but they see the same thing, so you identify them. Okay. Okay, so we have a simplicial the output, we have a simplicial complex, so-called protocol complex for the execution. But then we also need to have more things. So we need to, for example, to be able to express in this language the first thing we need to want to express is what is your task. So let's say I say this is my input, all possible 0, 1s combinations. Okay, this is my output, 0 and 1. But what is it that you want to achieve? So in other words, for each input, you need to tell which outputs are legal with this input. Not all outputs will be legal with all inputs, right? So like, for example, for the binary consensus, if I have some input, then there was a rule. The rule said, if they're all zeros, the only allowed output is 0. If they're all ones, the only allowed output is 1. If they're different, then all outputs are allowed. This was the rule. So you need to be able to express such a rule simplicially. So that's not a simplicial map, because if I have a simplex, I may have several simplexes I want to map it to. So that's what's called a carrier map. So in this map, each simplex would be mapped to a simplicial subcomplex. Okay. So there is some simplicial map called task specification map. Sorry, carrier map called task specification map. That's one thing you want to express. So just to express the task, not yet the protocol, you will need 3 things: the output, the input, and the specification map. Right? Which is standard things they do in distributed computing. They just don't formulate it simplically. They don't say simplicial complexes and carrier maps. They say set, and lists of sets and so on. But that's what it is. Okay. Then you would need an execution map which would connect the input complex with the protocol complex. In other words, if I have inputs, I would need to, for each possible input configuration, I would, in this global space of all possible executions, I would need to specify which executions are possible with this input. Okay, so that would be the execution map, and that would also be a carrier map. Then you need a decision map, which means when I have a protocol complex executions, now I have to make a decision. Okay, so I know all of my executions. And in each execution, I need to say, what is now the answer? So I need to assign the answers in the end for each one. So in the consequential model, you have one, and then in the end, you say the answer is this. But here you have many, and for each one, you need to say, what is now the answer? So that would be a simplicial map again, from the protocol complex to the output complex. And the last thing you would need to be able to say is that, okay, now you can formulate your task. You can formulate the protocol complex. You can say with which inputs, which executions are allowed. You can say for which executions, what is your answer. But you also need the final thing is to say that this protocol solves this task. Yeah. So now all of these associations were actually correct. That, in other words, that my protocol output satisfies the initial specification data which was supplied, right? So for this, you need a certain condition, which is kind of a commutativity condition on the simplicial level. So I think what I want to do is I want to, right. So let's see. Yeah, let me just think. So maybe what I should do, when should I finish? 25, right? We said. Yeah, something like that. Okay. So maybe the thing I do, I'll do the following. I'll say exactly what these conditions are, so that we have a model, which is general complicated model, and then I will have one picture showing exactly how this model works, exactly for this little protocol which I had for the communication channel, so you can actually see how this works. Okay. So right. So then so what I talked through now, we need to make it more rigorous, okay? So a simplicial formalization, notion of a task. So a distributed task. What is it in simplicial language? So we want to say something and forget about distributed computing after this if we want to. But of course, then we have some sort of model, kind of simplicial model. Okay. So first we have something called chromatic simplicial complex. That just means that we have a simplicial complex where we color the vertices. Okay, and always when we say colored the vertices means if the vertices are connected by an edge, they have different color. Okay. Okay. So first, if we have a chromatic simplicial complex, we call it rigid chromatic. If the complex is pure of dimension n, and the coloring is exactly the optimal one, so it's n+1 coloring. Okay, so you cannot do better than that, obviously, because you have n simplices in there. Okay, that's called rigid chromatic coloring. So if you have like a triangular structure, then you have colors 1, 2, 3, and then it repeats. You don't use 3 colors, so it's rigid. Once you fix it for one, you know the rest if it's connected by flips. Good. If you have 2 chromatic simplicial complexes and you have a carrier map between them, then we call it chromatic. If for all simplices, the image of the simplex is also pure, of dimension the same as the simplex, and has the same colors. Okay. So these chromatic things you need, because in all of this subject, you always have coloring of everything, input, output, everything, by the ID of the process. Okay, so each vertex will have the information, which may be quite complicated, but part of it will be the idea of the process. Okay, and clearly, if 2 are connected by an edge, they have different processes. So each process, it's not like he's doesn't decide. He hasn't decided what is 0 or 1. He has decided, so he never connects to himself. So this is, you always have the structure, rigid chromatic structure, and all of the maps are chromatic. So that's a mathematical condition, of course. Okay, so then a task, a distributed computing task, all of the standard tasks are like this, is a triple input-output complex, and the task specification map, where the input is a rigid chromatic input complex, output is also a rigid chromatic complex, and the task specification map is a chromatic carrier map. And furthermore, the vertices in input and output are uniquely defined by the color together with the label. So in other words, we don't repeat vertices where we say the processor 1 has a value 0. We have such a vertex, but we don't have 2 such vertices. Okay, so if we know the color, which is the name, and the input value or the view or whatever, that's it. That's only 1. Okay, so this is input-output complex, and the chromatic carrier, basically, that's a definition I already talked through when we were going through the previous slide. That's what we can call a task or distributed task. Okay. A protocol complex we can formalize like this. So again, it's a triple of 2 complexes and 1 carrier map. So the first one is again a rigid chromatic simplicial complex. The vertex is uniquely defined by color and label. That's the input complex. And the second one is the protocol complex itself. So that's a rigid chromatic simplicial complex, again, which has labels which we call views, because those are views of the processes. And then we have a carrier map, chromatic carrier map from the input to the protocol complex, and it satisfies this condition in the action preserving. So if we look at the 2 sigma and tau correspond to 2 input settings. If we take the intersection, then the executions, this intersection I see is the same as intersection of the executions of the complex. That's maybe a technical condition, but that's a condition we have for the for this. Okay, so the first one then formalizes the notion of the distributed task without yet talking about anything about solving them, and that formalizes the notion of an algorithm. So I think in the previous talk, I was talking about algorithm as a topological space. So here in this setting, algorithm is this triple, 2 simplicial complexes and the map between them, carrier map. The rest are some conditions on the simplicial complexes and on the carrier map. But if we forget about them, that's basically in the bottom line. That's our exactly. And using this language, we can then formalize what it means that protocol solves a task. Okay, so protocol solves a task in the consequential computing would be that algorithm solves the problem, computes the value. So solves the task means it works in each possible execution. There is a multitude of possible executions which are summarized in the protocol complex, and in each one it will produce the correct value. Or let's say there is not a single correct value, it would produce a value which satisfies the specifications of the task. So so that's this little condition in the end, right? So once we've formalized everything, the final condition is done very, very short. So it's just says on the left-hand side, we have delta of E of sigma. That just means that if we take the execution, which is the execution of sigma, then evaluate the output, then it lies in the specification. That's what it says. Delta is specification map. So in words, it just says each time the decision has been made, it satisfied the initial specification of the distributed task. That's a commuting thing. So for the example of the specific protocol which we had, so here we can start on left down. You have an edge 1, 2. This is just the input. This is the input complex. This means you have two processes arriving which want a communication channel assigned. So they have no other information than their IDs. So there is only one simplex. It's them, so to say. They have no inputs. Okay. Like I said, when we analyze all possibilities in this model, what happens if we communicate once? Each one writes first and then reads, right? So then there's these three possibilities. So reading from left to right, either the first one writes and reads, and the second one writes and reads, or they write together and then read together, or the second one writes and then the first one reads. So like I say, in our model, all we need to do is to specify an ordered partition of the two guys, and there are exactly three ordered partitions of two numbers, right? Either 1, 2, or 2, 1, or together. So these are the three executions, and the four vertices are the views. So what the first one, for example, it says that the first process sees only himself. Okay, that's what happens when he has the execution, when he arrived first. Jumping to the third one, it would say that is the first process sees both.
Here is not working well.
I see. I see.
Okay, so now we should be back.
Yeah, it should be. Yeah, controller should be fine, but I don't know. Yeah. Okay. All right. So so this is so let me finish with this slide. So we have input complex here, the protocol complex is on top, and the output complex is here. Okay, this is a possible output. This is the output complex of the task. So any assignments are allowed, but not both to the same channel, right? So the horizontal are lacking. So in the thick, I think it's visible. There is a thick three edges are thicker than the others. That's actually the decision map. Okay, and then that's a picture you have, right? For this, so this is how you would simplicity see that this protocol solves this task. That you would have this, and then you would need to check that it satisfies a certain commuting relation by the task specification map, right? But it does, because 1 maps always to 1 and 2 to 2. So that would be, so basically these 3 seek edges would be the decision map. Okay. All right. So again, so this kind of work has been summarized in this book of distributed computing through combinatorial topology with 2 courses of mine from US and from Mexico. And I think I'll just stop here. And yeah, okay.
Just one very good question, and then maybe a very short break where you can ask further questions. Okay, is there one? I'm intimidating you. No? So let's thank the speaker again and then ask questions later.
Okay.